So we will see the epicyclic gear train. Now in this epicyclic gear train, the axis of the shaft on which the gear is mounted may move related to another fixed axis. So in this epicyclic gear train, what is the difference? Whatever the gear trains we have seen up till now, in that the axis of the shafts on which the gears are mounted are fixed, but in this epicyclic gear train, the axis of the shaft on which one of the gear is mounted, may move related to the another fixed axis. And if this is the situation, then we can say that particular drive is epicyclic gear train. Now observe this particular case. In this, we are having a gear A which is mounted on the shaft and it rotates along the center point O1. Similarly, on the center point O1 there is another arm mounted, that is called as a arm C, and it can also rotate along this center point O1. So in this case, gear A and arm C is having a common axis of rotation, that is at O1. Similarly, gear B is mounted on the arm C and its axis of rotation is at O2. So we can say gear B meshes with gear A. Gear B is in mesh with gear A and has its axis of rotation, the arm C, at O2. Now if we consider this gear arm C is fixed, then in that case whatever the drive we are having, that is a simple drive, that is when the gear A will rotate in the clockwise direction, gear B will rotate in the anti-clockwise direction. But when this arm is able to rotate, then what will happen? The gear B will start rotating upon and around the gear A, following a epicyclic motion, and then this type of arrangement is called as a epicyclic gear train. How this epicyclic gear train looks like, we will see the video of this. Sorry. Okay, it will upload epicyclic gear train. And this epicyclic gear train, many times it is used in the differentials of an automobile, or in hoist pulleys, or in our lathe machines. And this particular arrangement is useful for transmitting the high velocity ratio when gear with the gear of moderate size. And this type of arrangement is very compact. So look over here how this particular arrangement works. We are having a first gear and then arm and then the second gear, and whatever the part traced out by the gear B, we can say this is an epicyclic type of path, and that's why it is called as an epicyclic gear train. Now for finding the velocities ratio of this type of epicyclic gear train, for finding the velocity ratio for the epicyclic gear train, there are two methods. One is called as a tabular method and another one is called as a algebraic method. We will see the tabular method. In this tabular method, suppose we are considering, let T is the number of ticks on gear A, while TB is number of ticks on gear B. Okay, now in first situation, what I will consider, that arm is fixed and gear A rotates through makes a 1 revolution. When the gear A makes 1 revolution, gear B will make a revolution of TA minus TB from the velocity ratio. As we know, I will write down over here, that is Na by Nb velocity ratio is equal to Tb by Ta. What we are considering, Na is 1, right? Na is 1, that is, it is making 1 revolution in 1 minute. Then Nb is equal to Tb by Ta. This tends to Nb is equal to Ta by Tb, right? So okay, I think my system got very slow, it is not responding. Just wait. Okay, I will clear all the things now. So what we are considering over here, the first condition we are first situation we are considering, that first of all the arm A is fixed and gear A makes a one rotation. In that case the gear B will make a rotation equal to minus Ta by Tb. Why we are considering the minus? Because if I assume that is anti-clockwise rotation of gear A is positive, then clockwise rotation will be considered as a negative. As gear A will start rotating in the anti-clockwise direction, gear B will start rotating in the anti-clockwise direction. As the sense of rotation is negative, that's why we are considering it negative. So first of all, in the first in this table I am considering arm C is fixed, that's why its rotation is 0. Gear A is making one revolution, that's why plus 1, and gear B in that case will rotate by minus Ta by Tb from the velocity ratio. Now we will consider second case, that is arm is fixed and gear A rotate through plus x revolutions. Initially we consider plus 1, now gear A is making a plus x revolution, and we will enter the second value of second rules, that is arm C is again fixed, gear A is making plus x rotation. If the gear A is making plus x rotation, then gear B will make a minus x multiplied by Ta divided by Tb rotation through the velocity ratios, by considering velocity ratio. Now we will add plus y revolutions to all the elements. We are considering that all whatever the elements are there are three elements over here, that is gear A, gear B and arm C. So all this will make 3. We will add a plus y revolution. So arm C plus y revolution, arm A plus y revolution, and gear B again plus y revolution. So total motion, that is adding the value of plus y revolution into the second row, that is total motion 0 plus y, that is plus y, plus x plus y, that is x plus y, and plus y minus x into t minus tv, that is minus y minus x into ta by tb. From this expression what we comes to know, what we get, that there are two unknowns, y, x and y. If any two values of these are known, then the third value can be find out from this equation. So if we are having a two values are known, the third values can be calculated in the for the epicyclic gear train. So these epicyclic gear trains are generally used in automobiles, in hoist, in pulley blocks, or in the differential of the automobile.